So before we go into operational amplifiers, let's define some terminology, and let's talk about amplifiers in general. So, so amplifiers in general, we start with looking at the model for an ideal amplifier. And the circuit model is shown below. This is a two-port system, which has an input port where a voltage Vin can be applied, and an output port. So I'm going to erase this little VI right there because you can't really see it very well. And an output port, Vout. And what it does is the output voltage produces the output port produces a voltage that is A times the input voltage Vin, where A is the amplification, or what we refer to as gain. Okay, so the units of A are in volts per volt. It's unitless. Volts per volt, or volts per millivolt, or whatever it is, but it's volts over volt, or volts over volts. And so a gain of 10 would say that if you provided 1 volt at the input, the output would have 10 volts, right? Or a gain of 10 if you provide 2 volts at the input, the output would be 20 volts. Okay, now this has, like, you know, this thing right here provides this input voltage Vin, and it's open circuit at the input terminals. In other words, the input current is 0, so there's no current flowing in here. In equals 0, and this whole thing, there's no resistance across this. So since there's no resistance there, Rin is equal to is infinite. Okay. What that means then is that there's no power drawn by the input. It doesn't draw any power from the source. As we're going to see, we're going to connect the source to this later. I'll just draw this in here for a moment here, but we might connect a little voltage source here. And an ideal amplifier won't load that down in any way. It won't draw any power from that device. Okay, turns out that that would be a good thing because it won't load the device down. It won't load the source down. Okay, so we'll see that in a moment. The sort of simplified model, simplified amplifier block, or maybe we'd actually just call this amplifier block diagram model. So if you look at block diagrams on where they just sort of show you, okay, here's an amplifier going, you know, from this point to this next point, and they tell you what the gain is. You can see that. I mean, if I just pull up a web search for a block diagram, for example, and let's say let's just see what we find if we pull up, like, let's say a speaker amplifier or something like that. So let's see what we find if we take a look here. Well, this isn't necessarily showing the exact, here we go. So here's a block diagram of some system. This particular system is a Class D audio amplifier. And it shows you some different blocks, and, you know, this stands for low pass filter, which we'll talk about later in the semester. ADC stands for analog to digital converter, and so on and so forth. But here, see this triangle right here? Triangles in general on a block diagram mean that block is an amplifier of some sort. It takes whatever the signal is entering it and produces another signal that is a faithful reproduction of that, that is either, you know, higher voltage or lower sometimes, or other properties. Okay, so so there's its block diagram symbol. Now, if the V out is connected to some load, we notice that there's, in the ideal amplifier, you don't see any resistance right here coming from that dependent source. So notice this, that the output is actually generated by a dependent voltage source, which we've seen earlier in the semester. And it has a gain A, and it's multiplying by the input voltage VI. But you don't see any output resistance here. So in fact, since there is none, the output resistance RO is 0 for an ideal amplifier. So ideal amplifier is that Rn is infinite, Ro is 0.